Okay, let's start. Let's not worry about others. Okay, so in the last session we have seen about two energies, the exchange energy and anisotropic energy, and now we will see about the domain wall energy and the magnetostrictive energy. Okay. So in a domain wall energy, as I said before, there are two domains. The domain wall is the one which separates uh, the two domains. Okay, so this domain, for example, in this one, it is pointing in this direction, and this is the another domain which is pointing in the opposite direction. The region in between is called as domain wall, and the width is called as the width of the domain wall. Usually, in magnetic materials, the width of this wall will be quite huge. Okay, especially for block wall. In block wall, the width will be like even in a nanometer scale. In a Neal wall, this is abrupt. The width will be domain wall width will be very small. So that is the difference between the block wall and the Neal wall. Okay. So what is happening in the domain wall region is that are like hundreds of atoms here. In hundreds of atoms, you will be having electrons which will be spinning in a different directions. So these electron spin or these atoms will slowly rotate, will slowly start rotating. Okay, so here, if you see in the domain wall, in this which is close to this domain, which is having more energy from this one, this domain. So all will be pointing in this direction. Slowly the energy will decrease. Okay? So what will happen is slowly it will start rotate, and then finally, so this domain wall along this region, it will be pointing in this direction. So this will take almost like a hundreds of atoms in between, slowly rotating. So that the energy between these two atoms are called as the domain wall energy. Okay. The fourth type of energy is called as a magnetostrictive energy, which is we have studied, I think, in the last semester. In the last semester, when we discussed about the ultrasonic production, in the ultrasonic production, we have used this magnetostrictive. Okay, so magnetostriction means, so on a ferromagnet, on a ferromagnetic material, if you apply some magnetic field, there will be a change in the size. So that is called as magnetostrictive energy. So imagine this is a ferromagnetic material. So by applying magnetic field, through applying electric field on this coil, so if you apply magnetic field, the length of this ferromagnet will increase. So this is called as magnetostrictive energy. Okay. So if you reverse the direction of this applied field, the length will contract again. So this will change between L plus delta L and then L. So if you apply some AC field, so this will oscillate. Okay, so this size change between L and L plus delta L will oscillate with the applied frequency. That is how you are producing your ultrasonic waves. That is what we have studied in the last semester. So that is one kind of energy which is required for this domain wall motion. So when you apply magnetic field on a ferromagnetic materials, these domains will start increasing in size, change in size. So that is called as magnetostrictive energy. Okay, so these are the four types of energies which are involved in the ferromagnetic domains. Okay, so that is called as domain theory. Okay, one is called as uh, exchange energy, anisotropic energy, and then domain wall energy and magnetostrictive energy. Okay, so these four energies. So if they ask, explain domain wall. okay, or a domain theory of ferromagnetism, you should explain up to this one. Okay, so you should write the domain wall motion, domain rotation, those two things, and then 4 types of energy involved in that part. So that is for domain theory. Sometimes, as for a 16-mark question, they will also include how the ferromagnetic hysteresis loop is described or explained using your domain theory. So for that, we should explain using this one. Okay, so this is a very simple example for a ferromagnetic hysteresis loop. As you know, hysteresis means lagging of some property. Okay, so we have when you wrote your ferroelectric material, okay, as an assignment, you wrote a ferroelectric hysteresis loop. Okay, and then on that one, on that assignment, most of you have put this hysteresis loop, where on the x-axis you put a magnetic field, and the y-axis it is magnetic magnetic moment. This is magnetic hysteresis loop. Okay, so for ferroelectric hysteresis loop, the x-axis, the applied field should be electric field, and then the y-axis should be the electric polarization. So know that difference. Hysteresis in general means a literal meaning. It is lagging behind of any property. Okay, here this is the lagging behind of domains. Okay, ferromagnetic moment. So that is called as ferromagnetic hysteresis loop. So what will happen? So this is your hysteresis loop. Okay, so this is your applied magnetic field and your magnetic moment along your y-axis. Okay, so in ferromagnetic material, as we have seen in domain theory, before applying magnetic field, all the domains, different domains, will be pointing in a different direction. So the net magnetic moment will be close to 0 or 0. Okay, so you will be in this region. Okay, so what will happen if you start increasing the applied magnetic field? So your magnetic moment will slowly start increasing. Okay, it will. This is called as virgin magnetic material. So this hasn't seen any magnetic field before. So for that materials, your hysteresis loop will be like this. Okay, so the net magnetic moment initially will be 0. So when you slowly increase your magnetic field, the moment will keep on increasing in this direction. And then if you keep on increasing the external Okay, so if you keep on increasing the magnetic moment, all the domains will align in the same direction. So you will have the net magnetic moment in this direction. So even if you keep on increasing the external magnetic field, the moment will not increase because all your domains are already aligned to the external magnetic field. So all your domains will be aligned in this direction. Okay. So when you decrease the magnetic field, so the moments will come back like this. It won't follow this region. Okay, it will come back and then it will follow this hysteresis loop shape. Okay, so what is happening there? Okay, so just we will take this region of your hysteresis loop. It is given here. Okay, so if you slowly increase your magnetic field, this will follow this region. So this region is called as reversible wall region. Okay, so in this region, if you decrease this magnetic field, the domain wall will go back to its original position. So the net magnetic moment will again be 0 because the energy is not sufficient to fix the domain wall on that region. So this is called as reversible region. Okay. So if you increase the field further, this region is called as irreversible domain wall. Okay, so if you decrease the field, applied magnetic field from this region, it will not follow this path. It will follow something like this. Okay, so this is called as irreversible wall displacement. It is because the wall will be pinned with some defects or some grains or some other impurities in the material. Okay, so this region is called as irreversible domain wall displacement region. Above this is called as domain rotation. Previously we have seen the process. There are two types of process. One is domain wall motion and then domain rotation. So by this magnetic field, up to this magnetic field, your domain wall motion would have been completed. Above this magnetic field, what will happen? So your domains will start rotating. Okay, so all the domains will start rotating, and then all these domains will align in the same direction. So this is called as saturation magnetization. That means all your domains have been saturated. So even you keep on increasing your magnetic field, the domains will always be the same magnetic moment because it has reached the saturation. If you decrease the magnetic moment, external magnetic moment, this will come back and it won't follow this path. Okay, it won't follow this path. It will go something like this. Okay, something like this. Okay, so this will go here and then follow this hysteresis loop shape. So this region, point D, this is called as a remnant field. Okay, so this region is called as saturated magnetization. Okay, MS, okay, saturated magnetization. This region is called as remnant magnetization, and this field is called as coercive field. That is the field required to make the magnetization zero, magnetic moment zero. So you should apply external magnetic field in the opposite direction to make the magnetic moment zero. So this field is called as coercive field. Okay. So in the case of single crystals, the saturation magnetization and the remnant magnetization will have the same value. Okay. So this will be like this. So you will have a rectangular hysteresis loop. That is what we are going to see in the next class for ferrites. Okay, for ferrite material. In the ceramics or other material, polycrystalline material, the remnant polarization will be smaller than the saturation magnetization. This is because of magnetic domains. There will be so many magnetic domains and impurities, other things in the ceramics and the polycrystals. Okay, so you should explain this. This is how we can explain the hysteresis using the domain theory. So in this region, the domain wall motion, and in this region, it is domain rotation. So if this question is asked in a 16-mark question, you should write up to this one. Okay, hysteresis, how we can explain hysteresis using domain theory. So with this part, like 95% of fourth unit is completed. There is one more small part which is called ferrites, which we will do it in the next class. Friday, we will meet in Zoom. Okay, so see, with the, if you have any doubt, you can post or you can clarify now. Okay, I will try to unmute. Okay, and then you just show any symbol or unmute you so that you can ask doubt. Otherwise, we can end this meeting. We will see you on Friday morning.